Rates of change. In this video, you'll learn how to calculate the average rate of change of a function over a specified period of time. You'll also learn how the average rate of change of an exponential function differs from that of a linear function. So the average rate of change measures how a function changes over an interval. To find the average rate of change of points A and B, we'll start by subtracting the outputs and then divide that by subtracting the inputs. For linear functions, the rate of change is constant. But for exponential functions, the rate of change varies across intervals. So let's look at an example. The table and graph shows the number of coffee shops worldwide in 2 years. So on the graph, we can see that the x-axis represents the years since 1987, and the y-axis represents the number of coffee shops. And in the table, the top row shows us the year, and the bottom row shows us the number of stores. We're going to find the average rate of change from 1987 to 1990. We'll use the table to find the average rate of change, and we'll call our first point in 1987 point A, and point B will be the year 1990. So we're going to take the formula for the rate of change, and we'll replace f of b with the output, which in our case is 84. Now we need to find the output of point A, and this would be 17. So we'll replace f of a with 17. Now we need the inputs. We can see the input of point B is 1990, and the input of point A is 1987. So now we could simplify our expression to find the rate of change. Subtracting 84 and 17 on top gives us a value of 67, and subtracting the years on the bottom gives us a value of 3. When we divide 67 by the 3 on the bottom, we get a rate of change of 22.3. Now let's find the average rate of change from 1987 to 1993. So point A will be the year 1987, and point B will be the year 1993. So we'll take our function for the rate of change, and our output of point B is 272. And our output for point A is 17. Now we'll look at the inputs on the bottom. The input of point B is 1993, and the input of point A is 1987. Now that everything's filled out, we can simplify this expression. We'll subtract 272 and 17 on top, which gives us a value of 255. On the bottom, we'll subtract the years 1993 and 1987, which gives us a value of 6. Dividing 255 by 6 gives us a rate of change of 42.5. Now let's find the average rate of change from the entire table, so from the year 1987 to 1997. Point A will still be the year 1987, but point B will be the end at 1997. So if we take our expression, we'll replace the output of B with 1412, and the output of A is 17. Now let's look at the inputs. The input of B is 1997, and the input of A is 1987. Now let's simplify our formula. Subtracting 1412 and 17 on top gives us a value of 1395, and subtracting the years on the bottom gives us a value of 10. So when we divide 1395 by 10, we'll get a rate of change of 139.5. In this example, we have a table that shows a function for the area covered in mold based on the days since the mold was spotted. We're going to find the average rate of change for the mold over all 6 days. So we'll start by calling point A day 0, and point B will be on the 6th day. So we'll take our formula and we'll replace the output with f of b with 64, and the output of A is 1. Now let's look at the inputs. The input of B is 6, and the input of A is 0. Now we can subtract and then divide our answers. 64 minus 1 gives us 63, and 6 minus 0 gives us 6. So when we divide these numbers, we get a rate of change of 10.5. So this is the average rate of change throughout the 6 days. But unlike a linear function, it doesn't mean that it will go up 10.5 each time. We can see that in days 0 to 1, it only went up by 1. And in days 1 to 2, it went up by 2. And then at the end, from days 5 to 6, it went up by 32. So the 10.5 just gives us the average of all 6 days. Here's another example. This graph represents the function p of t, which models the cost of producing 1 watt of solar energy from 1977 to 1988, where t is the year since 1977. So when we look at our graph, we can see that the x-axis represents the year since 1977, and the y-axis will tell us the dollars per watt. Claire says that in 1977 and 1982, the cost fell by about 12 per year, but in the second 5 years between 1983 and 1988, the cost fell by about 2 a year. We're going to show that Claire is correct. So let's look at 1977 to 1982 first. So we'll start with our value at 0, and we'll call this point A, which is 0 and then 80. 1982 is represented when x is 5. So point B will be 520. So we'll take our equation for the rate of change and fill in what we have. The output of point B is 20, and the output of point A is 80. Now let's look at the inputs. The input of B is 5, and the input of A is 0. So now we'll subtract and divide our differences. 20 minus 80 gives us negative 60, and 5 minus 0 gives us 5. So dividing negative 60 by 5 gives us a rate of change of negative 12. So far this matches what Claire said, and it did fall by 12 points. Now let's look at the years 1983 to 1988. 1983 is when x equals 6, so we'll call this point A, which is 615. 1988 happens after x is 11 years, so point B will be 11.4. Now we'll use these points to fill in our equation for the rate of change. The output of f of B is 4, and the output of f of A is 15. Now let's look at the inputs. We have 11 for B and 6 for A. So now we'll subtract and divide our answers. 4 minus 15 gives us negative 11, and 11 minus 6 gives us positive 5. When we divide the two, we get negative 2.2 as a rate of change. So it does fall about 2 a year, so Claire is correct in both of her assumptions. In this example, a study was conducted to analyze the deer population in a particular area. We'll let f be an exponential function that gives the population of deer t years after the study began. So we can represent this as f of t is equal to a times b to the t power. If the population of the function is increasing, then what must be true about the value of b and the function's rate of change? So we know the value of b tells us the rate of change. So this will be the growth or the decay factor. We know that it's exponential and that it's increasing. So the rate of change will start off small and then continue growing. Now let's recap what we've learned. When we calculate the rate of change for a linear function, the value is constant no matter what interval we looked at. But exponential functions have different rates of change for each interval, so we find the average. We find the average rate of change by dividing the difference of outputs by the difference of inputs.